So in order to define moment of inertia, we have to compare sigma F to sigma torque. So we know that the sum of the forces is equal to ma, and we can rewrite that as acceleration equals the sum of the forces over the mass. Now, we already know that for sigma torque, we know that that's equal to I alpha, which can be written as alpha equals sigma torque over I. So since both of these equations are in rather the same format, we can see the relationship that mass is resisting linear motion, just as the moment of inertia, is resisting rotational motion. So we can define moment of inertia as resisting rotational motion. So furthermore, we can go and see that the moment of inertia for any discrete point mass is mr squared. And if you have many discrete point masses, you can add them all up. So I can be the summation of all those discrete point masses. However, now let's take a different example where it's not a point mass. For example, we have a long rod. And so in order to find the moment of inertia about its pivot point, which is at the end, we define a certain small segment dx. And since this is of uniform mass density, we can write the statement lambda uniform mass density is equal to m over r, which is also equal to change in mass over change in r. And rewriting that, we get that lambda dr equals dm. There is the statement that the moment of inertia is equal to the integral of r squared dm, which is right here. Then, so we replace dm with our statement right here. And since lambda is a constant, we can take that out of the integral, and we can state that, and we can have our low bound to our upper bound as 0, which is right here at the end of the board, to its length, which we defined as L. So solving the integral, we get lambda 1/3 L cubed, and now we have to replace lambda with m over r, our r being L, and that's what we get 1/3 ml squared. Now let's take a different example. Pretend that now the pivot is at the center of mass. And so if the pivot's at the center of mass, we can use the parallel axis theorem in order to find that out. So the parallel axis theorem states that the moment of inertia at a pivot is equal to the moment of inertia at the center of mass plus md squared, where d is the distance from your initial pivot to the center of mass. So now let's look at a diagram. So our pivot was originally here, and now we have to take our center of mass. And the distance between the center of mass, assuming that the full length is L, is now L over 2. Now plugging in, we see that I found right here is 1/3 ml squared, which is equal to the moment of inertia at the center of mass plus m times L over 2 the whole squared. And then solving, we can see that ICN, the center of mass, plus 1/4 ml squared. And so we come up to the final answer that the moment of inertia at the center of mass is 1/12 ml squared.